Neural networks use quite a lot the concept of tensor. So from the point of view of the neural network, the tensor um is mostly a multidimensional array, although the mathematical concept of tensor is much richer because it has some internal properties about how what it behaves when you change coordinates and so on. But from the point of view of the neural networks, it's just an array. So you can have a 1D tensor in which all the numbers are an array, linear array of numbers, or 2D tensor like an image, 3D tensor, a 4D tensor. A 4D tensor would be a collection of 3D tensors. A 5D tensor would be a collection of 4D tensors, and so on. So we can think of tensors as high dimensional arrays. So for instance, this would be a scalar, would be a tensor of dimension 0. If you have a list of numbers, so an array of numbers, you would have a tensor of dimension 1 and length 3 in the one dimension. And then you can have a tensor that is an image or somehow a two-dimensional array. So you would have two axes. So the first one is dimension 0. So dimension 0 has length 3 and dimension 1 has length 2. Then you can have, for instance, a tensor of 4 dimensions. So in these 4 dimensions, so you would have 3 tensors, as we have said. So 3 cubes of data. In each one of the cubes of data, you would have 2 and then 4 and then 5 numbers. So would be a cube whose dimension is 2, 4 and 5, and you have 3 of those. So in the first axis you would have 3 cubes. Each one of the cube would be of this size. And how to arrange just beyond 3 dimensions, we cannot represent them. So it is just a convention of how to represent the tensors beyond 3 dimensions. But in general, it is not necessary to represent these high dimensional tensors, but you would have to think especially when you reshape the tensors. That is one of the operations we will do later. So you have to think how the data in the new space will be organized. So let's give an example. So let's say that we want to give we want to define a tensor of 3 dimensions. This is called rank 3. And then we fill it with these numbers. So it is just numbers from 0 to 29. So we have 30 numbers. The dimensions will be 3, 2, and 5. So length 3 in the first dimension, length 2 in the second dimension, length 5 in the last dimension. So in the first dimension, we will have 3 copies of images or 2D arrays of size 2 times 5. So we can represent them like this, we can represent them like this, like this. So these are different representations of the same object. And you can compute the slices. So for instance, the last dimension has 5 columns or 5 entries, 5 indexes. So we can, and they are always starting from 0. So they go from 0, 1, 2, 3, 4. So now we want the slice 4 of the last dimension and then keep all the other dimensions. So the way to say that, I think this is TensorFlow, but most libraries, they use the same syntax. So it is semicolon, semicolon, because we want all the indexes there, and then 4. And because we have specialized for one of the indexes, now the output tensor will have dimension 2, not dimension 3. So it is a slice through a tensor of dimension 3. So we have a two-dimensional tensor. And in this particular case, with this arrangement of data, so it would be in the last dimension we want 4. So that means these two, and these two. So in this representation here, for instance, we are accessing in this axis this one, and we are arranging them into a tensor that has dimension 3 and 2. So in the first dimension it is 3, in the second dimension it is 2. So these two numbers, they go to here, they are not vertical anymore. So vertical horizontal is just a convention of representation. So these arrangements of how the data are distributed in the cube, in the data cube, or the data tensor in general in any dimensions, and when you do slices and all that, can be quite confusing. Then yeah, so for instance here we have a tensor, four-dimensional tensor of these sizes, and this is axis 0, axis 2, axis 1, axis 2, axis 3. So this axis is the rank -1. So this is axis 3, rank 4, -1. So the typical axis orders for neural networks is the following. So you have, for instance, an image of various features. So you for each feature you have an image. So typically it is you have an image, and then you have the features, and then you have the batches here. So the first index is typically the batch, and all the rest is depends on your application. But for imaging applications, for instance, typical arrangement is this one: height, width, and then features. You can think of them as having different slices of different features. So this one would be feature 1, and you have an image of feature 1. This one would be an image of feature 2, an image of feature 3, and all those for all the data in the batch. So in the batch we have 3 examples. So these 3 examples are these 3 data cubes that we have in here. And then you can try to play a little bit with the different ways to define the tensors. So for instance, now this is the syntax of PyTorch. So you define PyTorch size 32. So what you have is a tensor that is one dimension, because it is just a set of scalars. So it is 32 scalars, and each scalar has dimension 0. So that is why the whole thing has only one dimension. Then, for instance, let's say you have a tensor of size 12 to 156. So typically the first one we have kept for the batch size. So we have 12 examples, and each one of those examples are one-dimensional arrays with a given number of features. So let's say that in your context, the number of features could be, for instance, number of channels of the image, height in pixels, width in pixels. So H times W gives you the number of pixels in the image, and then all of them are linearized, and you have 12 examples of those. Then this is another example where we have a three-dimensional tensor, 10 examples, so batch size equal 10, number of channels 1, and then number of features 2048. And for instance, this is typical. This is the typical arrangement when you go into a linear layer of the neural network. We will see the meaning of this thing later. And this is the typical arrangement when you do a convolution in one dimension, and again we will see what it means. For instance, when you have a recursive neural networks, the input to the recursive neural network is typically of this size. For instance, in a 2D convolutional network or layer, you would have batch size, number of channels, and then the size of the image. Or you can have, for instance, in convolution 3D, you can have batch size, the number of channels, and then X, Y, and Z, the sizes. Okay, what we said before, so you have 30 numbers in this tensor of size 3 times 2 times 5. So there are some good and bad reshapes. So a good reshape is, let's say that we go from 3, so from this 3 to 5, I think it was 3 to 5, yeah, this one, 3 to 5. So we go from the 3 to 5 tensor to a 310 tensor. So this reshaping, so all these reshapes, they all have 30 numbers, but in this reshaping, all the numbers coming from one of the slices, from one of the indexes in the original tensor, they're put together into another index. So all the yellow, orange points are here, all the blue, all the green points. And for instance, if we arrange in a 6 times 5, again, data coming from the same index, they are also close together in this reshaping. But if we do 5, 6, for instance, then the numbers, you see that the indexes now look awkward. So we still have the 30 numbers, but somehow this arrangement in space does not, or in the array, they do not somehow conform to the original arranging of numbers in the original tensor. The same here. So you can do a reshaping, changing 2 and 3, so the 5 keeps in the same location that these 2 and 3 swaps. So now the arrangements somehow look awkward. One of the indexes in these 2 dimensions, this dimension of size 2, we see they collect information coming from different areas of the original tensor. So all the tensor reshaping are possible, but the output somehow may keep the original geometrical meaning of the data or may not. And this reshaping is extremely complicated to have in mind how the data really behaves. So when you do reshaping, make sure that you are reshaping it in the way that you would like, and for that some printing part of the data could be very helpful. And an operation that we can do is this tensor concatenation. So let's say that we have a couple of tensors, and then we can decide in which dimension we want to concatenate. So we can put them together and form a new tensor. So these are two-dimensional tensors. So we can construct a single 3-dimensional tensor. And somehow this concatenation can be seen as the opposite of split and chunk. So you can see that you can play with the sizes and the organization of the data in memory. And the last operation we will see is this squeeze and unsqueeze. So let's say that you have a 2-dimensional tensor with this data, and then you put a dimension in front. So if you put a dimension in front, so it is changing the dimension. So this is 2, 2, if you want. So it is length 2 in the first dimension, length 2 in the second dimension. This one is 1 to 2. So we have put, so unsqueeze is putting an extra dimension of length 1 where you want. So if you put it at 0, so you are putting the new dimension in front. So then it will be 1 to 2. If you are putting this extra dimension of size 1, you put it in the middle, so between before 1, so this is before 0, before 1, before 2. So before 1, then the new tensor will be 2, 1, 2. And here the tensor will be 2, 2, 1. And somehow this is trying to represent that. And the data is still the same. The numbers are still 1, 2, 3, 4. But how to interpret that data is different. So you see here we have a single element, and that element has 2 times 2 dimension. So here we have 2 elements, and each one of those 2 elements have size 1 times 2, and this 1 times 2. And this one, that is 2 to 1. This is 2 to 1. We have a single element with this size. Okay, so these squeeze and squeeze, they are adding dimension of size 1 where you want, and it is these are operations that you need when you want to prepare your tensor to go into a layer that needs somehow some particular shape of the input tensor. Another operation with tensors is this flatten. So flattening is how you want to you have a high dimensional tensor, and you want to make it flat, so kind of 1D vector. So actually this can be quite flexible. So if you have a very high dimensional tensor, you see that by default we are going from the first dimension to the last dimension, but you can do it in the middle, so you can construct new tensors. And then there are multiple modes. So these multiple modes is how okay, we will have these numbers organized into a vector, but which is the organization of that vector. So for instance, this mode 1 flattening, so it is putting so it is organizing the data this way. So first this would be this index, and then index 3, and then these stacks of index 2, or you can put index 2 and then index 1, index 3. You can make any combination. So the final arrangement of the data will be different, although the numbers and the information will be exactly the same. And the last idea that I would like to convey here is that tensors that are high dimensional arrays have to live in some device, so either in the CPU or in the GPU. So for instance, here you have here the syntax to create a tensor in PyTorch. So you can detect whether there is some CUDA, and then if there is CUDA, you say my device is this CUDA or my device is the CPU, and you simply print what the device is. And then when you create a random tensor of size 2 times 2, so it will be 2-dimensional tensor, you can specify in which device you create that tensor. So if you create it in the GPU, the CPU will not see, and the opposite. So if you create it in the CPU, the GPU will not see that tensor. And then if you want to move one tensor from one device to another device, you can use this Y or the tensor to your new device. This would be all, I think, yeah, for the explanation of tensors. And next we will see the different layers that most libraries have. We will explain them, I think it is with PyTorch. And see you in the next video.